Assalamu alaikum dear students. This is Electrical Machines Lab and today we are going to perform lab number 5, that is three-phase connections of transformer. And we have actually four different type of connections, Y-Y, Y-Delta, Delta-Y and Delta-Delta. We are going to look at two connections out of these four, and these are Y-Y and Delta-Delta. Now, as you already know that we use three-phase system all over the world, and to use that three-phase system we need to come up with different configurations. So we have these different configurations by which we can connect the transformer. So as you know, a transformer has a primary side and it has a secondary side. So the primary side and the secondary side can be connected in these four ways. It, it can be connected in Y-Y. It can be connected in Y-Y means that the primary side is connected in Y configuration and the second side is also connected in Y configuration. On the other hand, if you talk about this one, the Y delta, it means the primary side is connected in Y connection and the secondary winding is connected in delta configuration. In the same way, we have this third one, which means the primary side is connected in delta and the secondary side is connected in Y. And this is the fourth one, which means the primary and secondary both are connected in delta configuration. So these are the two main connections, Y and delta. The Y is also called star, and but is usually known as a Y connection because it looks like a Y connection. If you look, this is the Y configuration, so it's just like a Y connection. This is why it's called a Y. On the other hand, this is the delta configuration because it looks like a delta. As you know, the delta symbol is just like this one, so that's why it is called delta configuration. Okay, so today we are going to connect the transformer in Y-Y connection and also in Delta-Delta connection. Okay, so first let us understand that why do we need three-phase power? Why do we use three-phase power? Why not 6 phases? Why don't we use 9 phases? Why don't we use 12 phases and onwards? This is one of the most frequently asked questions in interviews, that why do we use three-phase power? Why not 6? Why not 12? And so on. So the most frequent answer is that three-phase power, three phases give us more power than single phase. That's why we use three-phase power. Okay, if we follow this logic, then it means that the 6 phases will give us more power than 3 phases. In the same way, 12 phases will give us more power than 6 phases. So if it's all about more power, then why don't we use 6 phases or 12 phases? Why we are stuck with only 3 phases? So this is an incomplete answer, that we get more power in 3 phase, that's why we use 3 phase power. So this is just one reason. The complete answer is that it's also about economics. Uh, if uh, if you talk about 6 phases, then it's going to cost us accordingly. If you are going to use 12 powers, 12 phases, it will cost us more and more. So the economics play a very significant role here. So the 3 phase is the only combination in which we get a very high a cost to benefit ratio. So three-phase provide us the maximum cost to benefit ratio. On the other hand, if we talk about 6 phases, 12 phases, the cost to benefit ratio is lower because just because 6 phase provides us more power. On the other hand, it costs us more. So the cost to benefit ratio is less in case of 6 and 12 and onwards. So three phases is mostly suited because it gives us the best ratio of cost and power. So this is the reason we use three-phase power. We use three phases, not 6 and not 12 and not more than that. Another reason is that as we increase the number of phases, the corresponding number of the complexity will increase too much. And it's not just the cost of conductors itself. Uh, if you look at a distribution system, you have at the substation, you have circuit breakers, the corresponding to three phases, you have bus bars. So if we increase from three phases to six phases, for example, then there will also be cost of the three circuit breakers, the three bus bars. So, the overall cost is going to increase a lot. So this is the reason we don't use more phases. The three phases give us the best ratio of cost versus power. Okay, so the next thing is uh, the phase voltage and line voltage. So the phase voltage is basically uh, the voltage that we get in our homes is 230 volts. That is the phase voltage. If we talk about the line voltage will be under root 3 times the phase voltage. So if you plug 230 volts here, you will get around 400 volts. That will be the line voltage. So the characteristics of a star connection is that we have two different voltages. We have phase voltage and we have line voltage. On the other hand, if we talk about current, then we will have same current. The line current, phase voltage, both will be same in the star connection. On the other hand, if you look at the delta configuration, in the delta configuration we have the same voltage, the phase voltage and the line voltage, both are same, but the currents are different. So the phase current will be lower and the line voltage will be higher, just like in star connection, but that's for voltage. But in the case of delta, the difference in it is in the currents. So this is the overall summary of the star connection or Y connection exactly. Star and Y is the same thing as I discussed earlier. So this is the Y connection and this is the star connection. So one advantage of the Y connection is that we get two different voltages. On the other hand, if we talk about delta, we have two different currents. So both connections have their own benefits, and we will look at those benefits later. Okay, so let's get started with the Matlab Simulink. We will make these two configurations. We will make Wye-Wye configuration and we will also make the DeltaDelta configuration in the Matlab. In the lab number 6, we will explore the remaining two configurations, that is Y delta and delta Y. Okay, let's start with the first configuration, that is Wye-Wye configuration, and we will connect a transformer and a load in Wye-Wye configuration. So we need voltage source, We need a three-phase transformer. This is the single-phase transformer that we have been using in previous labs, and today we will use this one. This is the three-phase transformer. Then we need load RLC branch, and for measurements we need current measurement and voltage measurement. We also need RMS block. Then we need display block. Okay, let's start. Let's provide 120 volts. Frequency is 50 Hertz. We need 3 phase, so total 3 number of voltage sources. Now we have to provide the phase shift. We know that in 3-phase power the voltages are 120 degrees apart. So first one is at 0 degrees, second one will be at 120 degrees, and the third one will be 240 or 40 degrees, or you can also make it 120 degrees. It's the same thing. The difference is still 120 degrees, whether you make it 120 degrees or 240 degrees. So both are fine. Okay, so we have 3 sources. This is our transformer. Now this is the wiring diagram of Wye-Wye connection. Now look at this Wye-Wye connection. As you can see, each second leg is connected together. All the second wire is connected together to form a neutral point, and the other one we take as the 3 lines. So we have to connect one point of 3 individual voltage sources together. So it's like so we have connected the 3 phase. Now we have to connect the together that will form the neutral point. So this is how we connect our Y connection. Okay, now we have to provide a ground. Okay, so we have to use this one in the Simscape library. This ground is important because if you do not connect this ground, then you will not be able to measure the phase to ground voltages. Okay, so again here in the output side, okay, just to make things simple, just make it a simple resistor, 200 ohms. We need 3. Okay, so just like we connected the sources, we'll connect the load in the same way. 3 loads are connected to the transformer, and the other point will be connected together to form the neutral point or grounded point. We will provide the ground at the neutral point. So this is how we connect a Y configuration with respect to the transformer. Now let's open this transformer. Okay, Y can select any of these Y or Y neutral or Y grounded. It's just like same thing in the simulation, of course. In practical, it has a different meaning. And here we have the option of selecting 3 single phase transformer or a single 3-phase transformer. So it doesn't make any difference. You can select any of these, either 3 single phase transformers or 1 3-phase transformer. The parameters, you just have to change the frequency, make it 50 Hz. The rest of the properties are just same as we have used before. These properties are just like the single phase transformer that we have used earlier in previous labs. Okay, now we have to connect voltmeters and ammeters so that we can measure the voltages and currents in both primary side and at the secondary side. So we will need to connect 3 voltages for phase voltages and 3 for line voltages. So you have to connect 6 different voltmeters and 3 voltmeters or 3 ammeters for the currents. As I have already said, in the Y connections we have 2 different voltages. We have phase voltages and we have line voltages, but the current is same. The phase current and the line current are same in the Y connection. Okay, so instead of using these voltmeters and current measurements, there is a better option. we need to use this block three-phase VI measurement. This is a better option because it provides voltage and current measurements of all the three phases. We just have to place it between these three phases. You have to connect in at the secondary side too. Simple and easy. Okay, that's it. And now we have to, this is where we get the voltage VABC. The ABC represents the three phases, and here we will get the current IABC. So we will connect the RMS block to convert the voltage into the RMS, voltage and current both. So this is for voltage, and this is for current. Okay, now we need, because this will give us a three-phase quantity, three different voltages and three different currents. So we need a Dmax block that will split it into three different values. So you need to find a Dmax. Here is the Dmax. So there are just two outputs, but we need three outputs. So you can change that, make it 3. Now you can connect 3 displays that will give you 3 different voltages of 3 different phases. Okay, we have to do this for current. So let's make some room. Okay, and this is for the current and this is for the voltages. Okay, we need to do this on the secondary side too. So just copy this whole thing. That's it. Okay, so this is the Wye-Wye configuration of the transformer. We have connected 3 phase sources in Y connection, and then at the load side, at the secondary side of the transformer, we also connected a load in the Y configuration. So this is a Wye-Wye configuration. Now if you go to the properties of this measurement block, you have the option of phase to ground voltages and phase to phase voltages. So first we will measure the phase to ground voltages. Phase to ground, okay. We need a power GUI block. Okay, now we can run the simulation. Okay, so this is the voltages 125, 124, 129. So why we are getting a different readings? Okay, oh yeah, that's the problem here. We have to make sure that the frequencies are same in all the blocks, otherwise we will not get the correct results. Okay, now let's see. Okay, now we are getting the correct results. We are getting exactly 120 volts phase voltage at the primary side. We are getting this current at the primary side, and at the secondary side we are getting uh, around 48 voltages. So this is the phase voltages, and the current at the secondary side is greater because this is a step down transformer. So if the voltage is step, the current will be step up. So one thing increases, then one thing decreases, then the other thing will increase, uh, just to make the power balance. The power always stays the same, so this is the reason we are getting more current at the secondary side, because the voltage at the primary side is greater and the voltage at the secondary side is less than that. So okay, this is all good. Note down the readings here. So the phase voltage is 120, 120, 120. Okay, and phase current is 0.104. And do the same for here at the secondary side. For the line voltage, we have to change it to the phase to phase voltage. Phase to phase voltage and line voltage is the same thing, so do this for the load side too. Now we will get the line voltage. So As expected, we are getting 208 volts. This is exactly you will get if you multiply the phase voltage by root 3, you will get the line voltage. So if you multiply 120 volts by root 3, you will get exactly this voltage, that is 208 voltages. On the other hand, the currents are same. There is no change in the currents, there is only change in voltages. So this proves the theory behind the Y connection. The phase voltages and line voltages are different in Y configuration, but the phase voltage and line but the phase current and the line voltages are same. So this is why in the Y-Y connection we have same phase and same line current. So that's why you have only single type of current here, but we have different phase voltage and different line voltage. So this is 208, and so on. So fill up this whole table and then simply answer it. What is the voltage relationship between Y-Y configuration? Okay, so this is all about Y-Y configuration. The next thing is to make a delta-delta connection. So if we, this is the wiring diagram of our delta-delta connection. Now note here that the one side is connected to the other, the second side is connected to the third one, and third one is then connected to the first one. So this is just like a series connection, and there is no neutral in the delta-delta connection. So let's make this circuit. We have to do some changing. There will be no ground, so delete the ground. So the one leg of the voltage source is connected to the second leg, and the same way the second voltage source leg is connected to the third one, and again the third one is connected to the first one. This is exactly what happens in a delta connection. One leg is connected to the second one is connected to the third one, and third one is connected to the first one. So this will go here, this will go here. Let's make some room. Okay, and the third one is connected here. So each connection is between the middle point of the any two voltage sources. For example, this B is connected between these two, this C is connected between these two, and this A is connected between this and this. So this is how a delta connection looks like. So we have to do the same for the load side. So one leg is connected to the second one is connected to the third one, and then first one is connected to the third one is connected to the first one. if it doesn't make sense, if it looks complicated, then we can do the same just like we did in the here. We can make it that way. If it seems difficult to you, you just have to rotate it. So one phase is between this one, second one is between this point, and second one is between this point, just like we did here. So this is how we connect our delta connection. Okay, we have to change it to delta and this delta. Okay, next we have to set it to 200 newports. Okay, this is the line voltage. This is the line voltage that we got in the previous connection of Y-Y. So in the delta connection we have same phase and line voltages, but we have different line currents. So let's check here. The following voltage source blocks are in parallel or are connected in loops. Yes, they are connected in loops. So this is the problem. Now when I tried to search this problem, I came up with a simple solution, and that solution is we have to connect a small resistance, uh, let's say 1 ohm, or you can make it like 0.5 something, anything having a small value. So you have to connect these resistance between these points. So we have connected a small resistance between these sources that will solve our problem. So as you can see, we have 0.23 at the primary side and 0.57 at the secondary side. This voltage is, or this current is much greater if we compare it with the Y connection that you got earlier. So this is the line current. If you want to find out the phase current, then you don't have any option for that. If you select phase to ground, it will not work because there is no ground connection. So you cannot use this option. So the only option is to, you can either divide it by under root 3 because we have this formula here. So if you want the phase current, you have to divide the line current by root 3, or you can do another thing. You can provide it the phase voltage and measure the current. So if now this is the line current, and now we will get the phase current. So as you can see, the phase current is smaller than the line current. So in delta configuration, we get two different currents. We get line current and phase current. That's why you have, as you can see, in the delta-delta connection, we have line currents and phase currents, but we have only one voltage, that is 208 volts. So because there was not an option of phase currents, that's why we did this thing. Otherwise you have to provide the line voltage here, because in delta connection you have just single voltage, that is the line voltage. So this is the voltage in Y configuration, and this is the corresponding line current. For the phase current, you can divide it by under root 3. We are doing this just because we are doing this manually because we don't have the option in Matlab to measure the phase currents. We don't have the option, so that's why we did it. So anyways, this was the Wye-Wye the Delta configuration. So we have different line and phase currents, but we have same voltage. So find out the delta-delta configuration voltage relationship. This voltage relationship is basically as in the book we have three-phase transformer topic. Let's go to that topic. Here we have four different configurations. So this is the Wye-Wye configuration. The primary and secondary voltages are related to the phase voltages, and as you can see, the overall ratio is A, that is basically the turns ratio. So if you divide the line voltage and phase voltage, or phase voltage or primary and second voltage, you will get this ratio. So after getting these values, you will simply prove that this formula holds true for Wye-Wye connection and also for delta-delta connection. Both are same. So you will prove these equations here for this case and for this case. So this is all for lab number 5. In the lab number 6, we will explore the other two configurations, the Y-Delta configuration and Delta-Y configuration. Today we did Wye-Wye and Delta-Delta. So in the next lab, we will connect the transformer in these two configurations.